Well, David, you've had a busy week here in Toronto. You attended a couple events. So, what are some of the key takeaways that you've had, or things you've been hearing multiple times in all your conversations here?
I think the thing that's probably come through more than anything else is the fact that the arguments about whether or not hybrid encryption algorithms, so combining post-quantum and classical algorithms together, it seems that debate's finally settled and the decision's really been made that it's worth pursuing hybrid algorithms. This is quite interesting because there's already at least one standard for actually providing two keys, a classical and a post-quantum one, in a single certificate. And there's some others on the way as well. That's probably the biggest change. And yeah, it should be a good thing. I mean, people want to do it partly because everyone's perhaps a little bit worried about some of the newer algorithms, particularly the ones around lattice. The general feeling is that maths-wise, they really do stack up. So there shouldn't really be any concern, but it's natural there is concern. And the other thing is, from a migration point of view, being able to extend the use of existing infrastructure that's built around RSA and elliptic curve, but to be able to extend the lifetime of that by quantum hardening it, by introducing a second layer of keys, while it does make the attack surface a bit bigger and makes the implementation more complicated, there's all that PKI infrastructure in the background that you can actually reuse while you're actually working out how to migrate.
Nice. One of the things that we've talked about previously is, as we get this introduction to post-quantum cryptography, there's a difference between post-quantum cryptography and quantum cryptography. Could you give me a little introduction to that?
Yeah, that's correct. So post-quantum cryptography is really about algorithms that run on classical computers, the von Neumann architecture and that, which can be used to actually defend against quantum computers. So they represent a new range of algorithms which are not susceptible to attack from either known algorithms on classical computers or things like Shor's algorithm that running on quantum computers. But the emphasis there is that they actually run on classical computers. Quantum cryptography itself is really about cryptography in another realm almost, but which is based around using quantum effects. So the classic example of that is, for communication channels, using things like paired photons, a lot of spooky physics. They're quite entertaining, but yet a level of technology that's required, though, that's really only a government thing at this point. Certainly not commodity hardware or anything like that.
So if we take a look as the NIST standards are about to come out, the three big algorithms, what are the kind of the differences between them, and how might one be used versus one of the others?
Okay, so the three algorithms that we've got, one of them is a key encapsulation mechanism. So that's obviously different from the other two, which are both signature algorithms. In terms of how they actually work, though, you can kind of get a guess from the actual NIST names. Like the original names are Kyber, Dilithium, and Sphinx Plus. NIST, being a US government organization, likes to get into the acronyms. So there's MLDSA, which is what Dilithium is turning into, MLChem, which is what Kyber is turning into, and then SLH-DSA, which is what Sphinx Plus will turn into. Now, the ML in the ML and the ML-Chem and ML-DSA is symbolic of the fact that these are lattice-based algorithms. So ML-DSA and ML-Chem are both based on a set of mathematics derived from lattice theory. If you want, in a similar way that like elliptic curve or RSA are derived from the respective maths that they're derived from. Sphinx Plus, on the other hand, with the SLH, is actually derived from a modified version of, I guess, what you call a Merkle tree. It's built on hash structures, and that actually uses a different technology for actually creating signatures to what the dilithium algorithm does. And the handy thing about Sphinx Plus in that sense is that the research around the security of Sphinx Plus is a lot better understood. The technology is a lot older. And also, because these things are actually based on hash trees, you really only need to have enough infrastructure to actually compute a digital hash to actually implement your entire PKI. It doesn't come with anywhere near the overheads that, say, dilithium or Kyber actually has.